Hi everyone, welcome to our presentation. Today we'll be talking about the role of GIS in the routing of subsea cables and pipelines. I'm Holly Cairns and I'm a GIS specialist at Cathy.
I'm Paul Slater and I'm a technician at Cathy.
So an overview of our presentation. First of all, we'll be giving you an introduction to route engineering and what the hazards and processes are. We'll be going over the process of creating a constraints register and also how we define the constraint values. Then we will be given an overview of how we set up the GIS and CAD workspaces and how we integrate the two softwares. Finally, we'll provide an insight as to how we present the route and the constraints that are used for routing. So an introduction to route engineering. Route engineering is the process of converting an RPL into a product that is fit for installation. The process is done in GIS and CAD by integrating the strengths of the two softwares. Route engineering can be performed on inter-array, export, interconnector, telecoms or electrification cables, as well as pipelines and umbilicals. Each of the different projects has different routing inputs. We aim to create a product that adheres to the installation parameters and faces minimal risk during installation, and also reduces cable lengths as much as possible. Before we can begin routing, we need to receive the preliminary RPL from the client. Sometimes this will just be a corridor centerline, or it could be the client's first pass at route engineering. We need to understand how much data is available, as we require a geophysical survey to be able to undergo detailed route engineering. The better the data is, the more accurate product is created. We need to understand the planned installation method. If the product is a cable that is going to be buried, then the proposed installation tool should be known so that the width of the installation tool can be applied to the routing constraints. We also need to know the cable properties, as they inform the design parameters of the cable. So which seabed hazards can affect routing? First of all, bathymetry, as we need to be mindful of water depth if we are designing the cable crossing. Steep slopes, as anything over 10 degrees are often avoided to reduce risk of cable free span and to also increase tool stability. Boulders and debris are avoided, particularly in cable routing, as it can lead to an extensive removal campaign, or some may be too large to remove. Sound waves and mega ripples are avoided as they may be mobile and provide a risk of cable exposure or overburying. Superficial geology. We typically avoid areas of clay and glacial deposits as they are much more difficult to install a cable into. Magnetic targets may be indicative of a potential unexploded ordnance or possibly just a metal object on the seabed. Wrecks may be a PUXO risk, but can also have an archaeological significance. And existing assets. The crossing of existing assets may need to be considered if they are present. But where does GIS come into it? Well, GIS allows us to create a spatial workspace which brings together all of the hazards into one place and allows us to turn them from potential hazards to routing constraints, which forms the first step of our routing workflow. So step 1, all the client-supplied data is compiled into a GIS workspace. Once the available data is reviewed, a constraint register is set up and the constraint values are finalised during a workshop with the client. The constraint register contains hard and soft constraint values. Hard constraints are classed as those which may be avoided, whereas soft constraints should be avoided where feasible. The values may refer to the design parameters of the cable, such as the minimum bend radius, or the avoidance buffer to be applied to a wreck. Once the constraint register is complete, the constraints are buffered by their maximum dimension and half the width of the installation tool if the product that we are designing is a cable. The contacts are buffered by half the width of the installation tool, so that once the RPL has been finalised and the installation corridor is created, the corridor will then not intersect any of the spatial constraints. A web GIS can be created which shows all of the survey data and spatial constraints for the client, which is hosted through our own enterprise portal. The working RPL can also be loaded in to help the client visualize the routing progress. So why do we use CAD? Well, there is a seamless connection between Esri and AutoCAD products, which allows web mapping applications and GIS data to be imported into a CAD environment. Although GIS is much better for processing and visualizing constraints, it is easier to create a geometrically accurate product in CAD, as the software allows you to snap lines to circles, fill it between lines, and create S-bends through crossings. During the routing process, the DWG file can be added into GIS, and the changes made in CAD are automatically updated into GIS, meaning that you can view the route live against all of the constraints. My colleague Paul is now going to talk you through the process of designing a cable crossing.
Thanks, Holly. These slides show an example of an asset crossing. Here we can see the preliminary RPL is approaching an existing asset at an oblique angle. Ideally, we would like to optimize this to cross at or close to 90 degrees if space allows. Construction lines are created 50 meters from the asset and joined by their midpoints to create a perpendicular line. Circles are created tangentially to this line and the existing asset, with a 50-meter straight section joining them. 50-meter straight and 100-meter radii turning circles have been agreed in the constraints register. The construction lines for this side of the crossing are trimmed and joined together to create a polyline section. Ideally, the crossing will be symmetrical, so the geometry can be rotated and copied through 180 degrees, then the two polylines joined together. We should have checked the constraints mapping before designing this crossing. As you can see, there are a number of boulders and a rock outcrop. Our cable skims the rock outcrop, which could be problematic to cabling operations. We should try to avoid this. If we need any further information on these constraints, the crossing can be viewed live in an ArcPro workspace, which allows us to view all of the attributes related to these obstructions. Here we can create a construction line tangential to the crossing radius and the boulder, which should give us the smoothest transition and shortest length. This is then joined to the RPL by a 100-meter circle. The construction lines and RPL are trimmed and joined together to create a continuous polyline. Crossings are often the most complex part of a cable routing project. We tend to design these first, along with the cable ends, then fill in the gaps. Once the whole RPL is designed, we can export this to shapefile or geodatabase directly from AutoCAD map. This can then be instantly used in GIS to calculate geometry attributes and check for clashes with constraints.
Thanks, Paul. So once the finished product is exported from CAD into shapefile format, the metadata is populated and the finished product is sent to the client, along with other deliverables. These may include a technical note, route listings, and alignment charts, which we automate in ArcGIS Pro. We also provide a list of all the contacts found within the installation corridor, as it is often impossible to avoid all seabed features without creating a bendy, uninstallable route. So in summary, route engineering is the process of converting an RPL to an installable product, which accounts for the cable design parameters and nearby spatial constraints. The route is kept as short as is feasible to minimize costs. The spatial constraints are analysed in desktop GIS and can be rolled out to the client in a WebGIS environment to allow them access to the routing process. The route is designed in CAD and brought back into GIS thanks to the seamless relationship between the two softwares. Thanks for listening, everyone.
Thank you.